this is David Van Vranken here at UC Irvine, here to start the 21st lecture in the Chemistry 51C series in the spring of 2020. It's a quarter where we're doing remote instruction. I wanted to start off my lecture by talking about a term that I hope you'll never hear again, unless someday you end up teaching the history of clinical oncology. Someone who's very close to me is undergoing chemotherapy, has been undergoing chemotherapy for a non-Hodgkin's lymphoma, and went through a treatment regimen commonly known as RCHOP. And I want to talk about this RCHOP term. RCHOP is a regimen of drugs that's composed of 5 different anti-cancer compounds. One of them is an antibody called rituximab that targets B cells, a type of white blood cells that have the CD20 antigen on the surface called rituximab. Gets the immune system to help try to kill the cancer cells. There's also a whole chemical mixture that has to do with the letters CHOP. Let's go ahead and talk about those chemical components to this treatment regimen. The first one is cyclophosphamide. It's a drug I'll tell you more about just shortly. The other components, the C is cyclophosphamide. The H is for a compound doxorubicin. I think they were trying to make the acronym work out, so they called it H for another name, hydroxydonomycin. That's the less common phrase for doxorubicin. Another component of this RCHOP regimen is oncovin. It's a vinca alkaloid that comes from a periwinkle plant, I believe, that's very potent at targeting tubulin polymerization, which is essential for dragging chromosomes to opposite sides of dividing cells. And then finally, a steroid. It's a derivative of cortisone, like the steroid cream you buy for itching, but it suppresses immune function, and B cells, white blood cells are definitely immune cells. I wanted to talk more about cyclophosphamide. All of these compounds are designed to just try to kill all the white blood cells. And the hope is always that the patient can survive. If you can just hammer down these B cells, the white blood cells, it just will not stop growing. So the origin of this, let's talk about cyclophosphamide. Cyclophosphamide is a derivative of a class of molecules called chemical mustards. And molecules that have these chloroethyl groups, chlorine, CH2 attached to a heteroatom with a lone pair, these had their origins back in World War I. They were used as chemical weapons that would volatilize these aerosols of things like mustard gas, absolutely horrific compounds. And they're designed so that the lone pair of this, the nucleophilic lone pair on sulfur in mustard gas would attack the neighboring chloride to make a 3-membered ring, right? If you draw the lone pair starting from the sulfur, you end up forming a new sulfur carbon bond, and it is very strained. That ring wants to open back up. I am so sorry, I left off the positive charge here, but on the sulfonium ion. But this thing wants to open back up and relieve that ring strain. It realizes, oh my gosh, I made a mistake, I'm strained. And so nucleophiles will attack, nucleophiles like proteins and nucleophiles like DNA. And so anybody who's exposed to mustard gas, they end up being blinded. It targets, it's just really vicious. It generates 2 equivalents of hydrochloric acid every time a nucleophile attacks, which causes even more damage. Your lungs fill up with fluid, you're blind, and you just need other soldiers and other people to take care of you once you've been exposed to mustard gas. Some very enterprising physician, I assume it's a physician, noted that soldiers who were exposed to mustard gas had low white blood cell counts. It turns out that these chemical mustards were causing the death of white blood cells. And if you're an MD who studies leukemia patients whose white blood cells are growing uncontrolled, then any agent that kills white blood cells would be really miraculous. And so this led these mustard gas that was used in World War I led to the development of the first DNA alkylating agents for the mustard type alkylating agents for the treatment of cancer, like mustargen. They replace the sulfur with a methylamino group, and the lone pairs on nitrogen can cyclize around. We'll talk about that shortly. And then in the late 1950s, a better derivative, maybe I think it's better tolerated derivative because it requires metabolism, called cyclophosphamide was developed. So let's go ahead and talk about this drug that was introduced in 1959 called cyclophosphamide, that is a component of this R-CHOP regimen. It's the C in R-CHOP. So here's cyclophosphamide, introduced in 1959, approved. So it's an old drug. It doesn't just work on its own, because there's a lone pair here on the nitrogen that is deactivated by something like resonance donation into the phosphoryl group. And as long as this phosphoryl group is in this form, it's hard for the nitrogen lone pairs to have the nucleophilicity it needs to cyclize around. But what happens is, as this floats around in the bloodstream, if you take it orally, it'll go, you don't have to worry about it being active as much on the GI tract as probably the mechlorethamine. Or if you take this IV, it goes right into the bloodstream, but it has to pass through the liver. This requires first pass metabolism in the liver that hydroxylates right, it puts an oxygen atom right between the H and the C here next to the amino group. And then this opens up. There's an equilibrium that is related to the mechanism that you learned for aminium ion formation. It goes through the reverse. It's kind of the reverse of imine formation. And you generate equilibrium amounts of this beta alkoxyaldehyde. This readily undergoes an E1CV elimination mechanism where you deprotonate at this position and then eliminates out the oxygen. So you get two products out of this that are both toxic to cells. One of them is this small molecule acrolein that is a very reactive electrophile for Michael addition reactions or conjugate addition or imine formation, and that ends up damaging and covalently reacting with proteins. The other component that you get now has very much the reactivity of that sulfur mustard that was used in World War I. And when this enters cells, the nitrogen lone pairs will push out the chlorine and make a strained three-membered aziridinium ring, a three-membered ring with an N+, so strained it wants to reopen. Nucleophiles will open that up. And when proteins react with that, you just get regular protein damage. But when DNA reacts, you have the potential to form crosslinks between two strands of DNA. And for rapidly dividing cells, there is no type of damage more lethal than cross-linking DNA strands. Cells try to sort apart chromosomes and duplicate DNA during the S phase of the cell cycle. And if a cell that's rapidly dividing discovers that it has crosslinks between the two DNA chains, the cell will immediately commit suicide. Absolutely a lethal covalent reaction. And that's the way cyclophosphamide works. Okay, so chapter 25 is the organic chemistry of amines. And I want to try to summarize two main themes that are going on in this chapter. We're interested in amines that have a lone pair on them. And that lone pair means that the amines can undergo two types of reactions. One of them is very fast, and that's acid-base proton transfer reactions. So whenever you put amines in aqueous solutions, you're thinking about like Henderson-Hasselbalch equation and very fast equilibria to generate equilibrium amounts of these two species. It goes forwards, it goes backwards, forwards and backwards. So when you have, depending on the pH of your solution, if you're in an aqueous solution, you have to think about this fast equilibrium, back and forth, back and forth, back and forth, so fast. But there are slower processes that we have to think about. And that's the formation of bonds, and especially formation of bonds to carbon. Amine lone pairs are nucleophilic. They are more nucleophilic than a corresponding oxygen lone pair. Ethers are not nucleophilic. Amines are somewhere on the order of 11 orders of magnitude, like 100 billion times more nucleophilic than an oxygen lone pair. It's not even close. And so we have to consider the potential that amines can do SN2 reactions on alkyl halides, on alkyl tosylates, on things that have good leaving groups and are not hindered. They can do SN2. And so when you do that, you'll initially generate an ammonium ion with if you use the lone pair to form a bond, you won't have a lone pair there anymore. And so a lot of what happens after this depends on whether R has an H still attached there. So that's the theme for this chapter. We have to think about this very fast process of acid-base equilibrium and what are the implications for that acid-base equilibrium. And then we have to think about, as we keep in mind these acid-base equilibria, then what's up with these other potential reactions where amine lone pairs can act as nucleophiles. And we've already talked about amine lone pairs attacking, for example, carbonyls in imine forming reactions like that, and carbonyl condensation reactions. Now I want to contrast amines, A-M-I-N-E-S. Oh, and let me just come back to here and try to paint a picture that in general, when amine does an alkylation reaction, an SN2 type process to form an ammonium, that bond is there, it's stuck. You don't go backwards generally. Whereas with protonation, fast and reversible, but alkylation, forming an NC bond, a bond to carbon, that you're kind of stuck there in most cases. Now I want to contrast the reactivity of amines, where you have alkyl groups on nitrogen, maybe an aryl group on the nitrogen, with a nitrogen atom that has a carbonyl. That is a completely different type of functional group. When you put a carbonyl group here, that lone pair is not basic at all, ever. There is no reaction you will ever see where an amide nitrogen lone pair with a carbonyl next to the nitrogen attacks anything. It's not basic, it is not nucleophilic. The reason is that if you've got some acid somewhere floating around, that lone pair is already donating, or if you have an electrophile, that lone pair is already donating into something. It's attacking the carbonyl that's right next door. So let me draw that resonance structure. Don't use amide lone pairs to attack things. They're already attacking something, right? This is the other way to represent an amide. Right? Linus Pauling said, oh, you know, if you want to think about how much do each of these resonance structures contribute to the character of an amide, Linus Pauling said, well, you know, that nitrogen carbon, that's about a 40% double bond. Why would you ever use N+ to attack something? You wouldn't. So don't ever use the lone pair on an amide to attack anything, at least in the chemistry 51C series. You're not going to see that happen. Okay, but regular amines that have alkyl groups, doesn't matter whether it's cyclic, there's lots of cyclic amines. We're going to see those attack plenty of things. We're going to start off by talking about, usually the first part of the book talks about structure and bonding. And I'm going to take a little bit of time and talk about the structure and bonding in amines. A lot of this was in the 5th edition of the Gorzynski-Smith textbook. In chapter 5, it talked about structure and bonding and talked about stereochemistry and stereochemical configuration. And I want to talk about that issue. Here's a common molecule, amphetamine, also sold as Adderall for ADD, or taken recreationally. And you notice here in this molecule amphetamine, I've got a stereogenic center. I've got an sp3 hybridized carbon atom. Let me go ahead and draw a dot there. That's a stereogenic center. And that stereogenic center can have an R or S configuration associated with it. So let me go ahead and just highlight the fact that that's a stereogenic center. I'll write that down here. Stereogenic center, that little thing right there. I don't want to put an arrow there, but you get the idea. But when you look at the nitrogen, it's also sp3 hybridized, and it has a lone pair there that takes up space. You might have learned something called valence shell electron pair repulsion theory for something, I don't know, but it suggests that this nitrogen is going to be tetrahedral with 4 different things on it, if you want to think about the lone pair as a thing. It's got an H, it's got this phenethyl type group here, and it's got a methyl, and it's got a lone pair. 4 things means it ought to be stereogenic, but in our class, we're not going to consider these stereogenic centers, these nitrogen lone pairs on aliphatic amines, even though they're tetrahedral. And let's talk about why. And we have a more precise term. If we want to be really correct, we wouldn't talk about stereogenicity, because it is actually stereogenic. The issue is that it is not configurationally stable. The R or S configuration of this amine is not stable. That's because when you have 3 different substituents on an alkylamine and a lone pair, this lone pair can rapidly interconvert between R and S. So fast, thousands of times a second. You have no chance to isolate any molecule based on whether it has, or if it's a regular acyclic amine, based on whether it has an RS configuration on that nitrogen. So there's a very rapid equilibrium that goes through a transition state. I guess I'll try to draw that transition state here. I'm not trying to imply stereochemistry with bold and wedge. I'm just trying to draw closer things, darker. And then back here, I've got the H. So this very rapidly isomerizes through I'll draw each electron in each lobe of the p orbital through a planar intermediate, through a planar nitrogen atom that is trigonal bipyramidal. There is no such thing as R or S here. It's completely lost. Once it gets to this transition state, it can easily go right back where it came from or reflip over this way. You have no control over this. This is so fast. You can't stop this. This has now lost all configurational memory when it reaches this transition state. It's got 3 atoms in plane. So amines are not configurationally stable. This nitrogen atom here on methamphetamine is rapidly interconverting between R and S at typical room temperature conditions you would work with in a laboratory setting. So we don't consider that. We're not in Chem 51. We'll consider it not stereogenic. So I'll just write not. So don't worry about a sign. If I ask you to identify, note stereochemistry in the existence of stereoisomers, you would not select a nitrogen as being a stereogenic center in our course. But again, the more precise term would be to say that it's not configurationally stable. They don't really introduce much of that in the early parts of the textbooks. I don't want to focus too much on that, on this issue of configurational stability. All right, we have to talk a little bit about nomenclature. I don't ask you questions about IUPAC nomenclature. I don't give you the structures of molecules and say, tell me the IUPAC name. I don't give you an IUPAC name and say, draw the structure of the molecule. But I expect you to know the names of common functional groups. We use that language of knowing the names of functional groups: amides, ketones, enamines, esters, enolates. You have to know the names of those functional groups that we cover. One type of functional group naming is to subcategorize things like alcohols or alkyl halides into being primary, secondary, or tertiary. We use the same language for carbocations. Let me remind you that a primary alcohol is an alcohol where the carbon atom has just 1 alkyl group and 2 H's. And a secondary alcohol is an alcohol that has 2 alkyl groups on that carbon. Here's the carbon atom that we're talking about. And 1 H. And then a tertiary alcohol or a tertiary alkyl halide or a tertiary carbocation has 3 alkyl groups on that carbon atom that we're talking about. But what you're going to find in this chapter is that it gets confusing, because when I look at ethylamine that has 1 alkyl group on the carbon atom, I think it makes sense here, for the wrong reasons, that should be called a primary amine. And then we come over here to this one with an isopropyl group on the amine, and we look at the number of things that are attached, but unfortunately, this is still a primary amine. And when we come over here to this T-butyl substituted amine, that's still a primary amine. So everything you learned about the naming of carbocations, alkyl chlorides, alcohols goes right out the window. We use the nomenclature, primary, secondary, and tertiary, to refer to the nitrogen atom. We're looking at how many alkyl groups and how many H's are attached to the nitrogen atom. And if you have a carbonyl attached to the nitrogen, it's not even called an amine anymore. It's called an amide. That's a different functional group. So we're talking about amines here. So let's go ahead and draw out. What would it look like if you had a secondary alkylamine? Well, you have to put another substituent here, alkyl group. Not all H's, but you have to put another substituent. I'll just put a methyl group here on this nitrogen. That's a secondary amine. And it doesn't matter what we have over here. It could be ethyl, methyl, T-butyl. I'll put the T-butyl on there. So this is a primary, or sorry, this is a secondary alkylamine because it has 2 groups on the nitrogen and 1 H. That's secondary. There we go. And if you want to have a tertiary amine, now we have to have 3 alkyl groups on there. And it doesn't matter what those alkyl groups are, just as long as there's 3 alkyl groups. We would refer to this as a tertiary amine. So you have to look at the nitrogen atom, not at the carbon atom that's attached to the amine, in order to decide whether an amine is primary, secondary, or tertiary. So it's going to be confusing to you, since everything up until the last few weeks of the Chem 51 year-long course, suddenly at the last moment we're changing what we're discussing. Amines are basic. They're usually smelly. When we work with amines in the lab, they have a strong, not like sulfur compounds. You know, the smell of dead fish or putrefying flesh that's amines, usually diamines, like some molecules like putrescine. Amines are basic. Remember, the most common base that I use in the organic chemistry laboratory is triethylamine, because it's soluble in all organic solvents, whereas sodium hydroxide is not. So we don't use sodium hydroxide that often as a base for organic chemistry experiments, just because it's kind of nice when your reagents actually dissolve in your reaction solution. Okay, let's go ahead and talk about some spectroscopic properties of amines. I always seem to put, again, I don't tell you what's going to be on my exams, but you know, if you look at my past exams, I usually put a spectroscopy question on there, and I'd like you to know the basics of spectroscopy. I'm not going to ask you about the mass spectrometry of amines. Maybe that was important in the old days when mass spectrometers would blast the heck out of molecules until they fell apart and you look at the fragments. That's not what we do. You can just assume anytime I give you a molecular formula that has come from a mass spectrometry experiment. So if I say, what's the structure of the product? Use spectroscopy, and here's the molecular formula. It's my intention to mean that they got the molecular formula from mass spectrometry. There's one use. IR is just not that useful for assigning structures to organic molecules. It's a good quantitative technique. You can attach an IR spectrometer to a telescope and say something about the light, you know, what functional groups are present in the light coming from distant galaxies. But most of the things you use IR spectroscopy to identify in an organic molecule, you can do more easily with NMR and IR. But here's one way I think that IR spectroscopy is useful in a way that it is not for NMR, or certainly not for C13. Okay, so when you have OHs or NHs, stretches, you know, that stretch for an OH or an NH bond, those usually occur down in this region above 3,000 wave numbers. And a nitrogen atom's lighter, but also because of hydrogen bonding, amines hydrogen bond like alcohols. And because there's so many different ways to hydrogen bond, and hydrogen bonds form and break so quickly and shift around, you get like 1,000 different frequencies for each NH, because there's so many different ways that it's hydrogen bonding and forming hydrogen bonds. You see all of those at the same time in your ensemble of molecules. And so you get these big lumps. You get big lumps usually for alcohol OHs, for amine NHs, and certainly carboxylic acids. You get these big, huge lumps because hydrogen bonding is so powerful. But there's usually a little peak that shows up quite often for alkylamine NHs. And depending on whether you have a dialkylamine with one H or a primary amine with 2 H's, so secondary versus primary, you'll see a different number. I probably should have. So it correlates with the number of NHs. If you look, there's a little peak that pokes above this big blob. And for dialkylamines that have a single NH, you get one of those peaks. But then for primary amines, monoalkylamines that have 2 NHs, you get 2 of those little blips. That's kind of cool, and it's kind of useful. And you can't get that kind of information just by looking at a proton NMR or any other type of spectroscopy. So that's pretty useful. One of the challenges with taking IR spectra of amines is that they are almost always contaminated with a little water. And water absorbs so strongly in the infrared that a tiny amount, 1% of the water that's contaminating your amine will lead to this big blob. And that big lump will often hide those little NH stretches. So you have to have really pure amines that are water-free in order to see those little blips. I wouldn't give you an IR spectrum or I would try not to, certainly not in, try to make sure I didn't give you an IR spectrum that was contaminated by water. But when you're in the lab, it's very hard to get rid of that extra water in your amine sample that will cover up those little blips, those useful little blips. What about these other types of spectroscopy for amines? How do you tell by looking at a C13 or a proton NMR whether you've got an amine in your molecule? Can't do it. It's unfortunate. Let's go and take a look at what's the C13 spectroscopy range for amines. Here's a molecule with ethyl, methyl, and a phenyl group on an amine. It's an aniline derivative. And if you look at the chemical shifts of these carbon atoms that are right next to amines, it's like 47, 37. That's right where carbon atoms always show, no matter what they're attached to. You can't even tell just based on those chemical shifts that they're attached to a nitrogen atom. If I come over here to propylethylamine, this is a secondary amine, all of these shifts, they're kind of below 100. You can't tell whether they're attached to nitrogen or oxygen. You don't get any information out of that. You're best off just looking at the molecular formula and noting there's a nitrogen in there. And it's the possibility there's an amine, but you can't look at the chemical shift range for proton NMR and say, oh, there must be for a carbon NMR and say there must be an amine on there. And it's the same for trying to tell in the proton NMR, do I have a nitrogen attached to something? If you look at the chemical shift range for this proton right here attached to the amino group, depending on how much hydrogen bond, things that are hydrogen bonded ended up getting shift to, I hope I'm doing this the right direction on the camera, to higher parts per million. We call it downfield when you have lots of hydrogen bonding. Or if you have a compound that's very dilute and has very little hydrogen bonding, it'll appear farther upfield at lower ppm. And it can shift all over the place depending on the concentration of amine for your NMR sample. So you can't really look at the chemical shift of an H and know whether it's attached to a nitrogen like an amine. It's just, usually what you do look for is that those H's attached to amines are usually broadened a bit. Anything that has hydrogen bond, it leads to broader peaks in the proton NMR. So that's usually something to look for. Now the CH that's next to the amino group, it occurs in the same region as everything else. You wouldn't know that this CH2 group is attached to an amine just because it appears at 2.8 ppm or somewhere around that region. So it's not very useful. And then the splitting patterns, anything that's hydrogen bonded, spends its time forming hydrogen bonds that go back and forth, lots of different hydrogen bonding configurations, it's shifting around all the time. And so the expectation for you, except under very special conditions, is that these NHs should not split the neighboring atoms, that the NH here will not split the CH2. The only splitting that this CH2 would get would be from the CH3 next door. And that's the same thing that you saw with alcohols, which are very heavily hydrogen bonded, is you usually, at typical NMR concentrations, you don't see splitting between the CHs and the OH. The OH doesn't split its neighbors. You'd have to go to super dilute, crazy, weird conditions to see that splitting, or have a structure that makes it hard for it to hydrogen bond, or only forms a very specific hydrogen bond. Okay, spectroscopy. That was a bit of a letdown, but I like that cool IR thing with one little blip or two little blips going down. That was I think that's kind of a cool feature of amine spectroscopy. Now the book always seems to have some section on interesting amines, and I'm not going to ask you to memorize the names of common amines and then say, tell me what the structures are on any test I give. But usually, if I think about the coolest compounds in organic chemistry, it's illegal drugs or drugs. And when I think of illegal drugs, I'm thinking amines. Amines, like amines are, if you want to think about drugs or even pharmaceuticals, I think amines. let's go and take a look at some of the amines that you've heard of, drugs that you've heard of, natural compounds that you've heard of. So one characteristic of amines is that they tend to have the ending INE on the end of a compound that contains an amino group. And as soon as I hear that a compound has an amino group, I'm thinking, okay, it's a little bit basic. I ought to be able to protonate that in acidic conditions, so I ought to be able to dissolve it in slightly acidic media or at neutral pH. If it's soluble, it's mostly protonated. So hearing that ending INE on the name of a molecule tells me there's a basic amine. Here's a natural product called conaine. It's an alkaloid. That's a nitrogen-containing plant compound. This one comes from hemlock. That's what Socrates drank. I don't know if that's mythology or true, but in order, he was forced to commit suicide by drinking a glass of, or whatever, a goblet of conaine. That doesn't look very potent to me. I can't imagine how much he had to drink. Probably he got nauseous drinking a compound with such low potency. Here's an everyday compound that unfortunately is an amine that is still very common, not just Greek history. And that's nicotine. This is the addictive substance and the stimulant that they have inside of tobacco products. And of course, it contains two potentially basic functional groups. It contains an amine, like this one here. Here's the amino group. That's not really amine down here. That's a pyridine. You wouldn't call that an amine. It's a nitrogen-containing heterocycle. You know that for some reactions, like acylation of alcohols, we add pyridine to soak up HCl. This pyridine nitrogen is about 100,000 times less basic than an alkylamine like nitrogen, like triethylamine or this sp3 hybridized amine. So you see that ending on there, the ene ending, nicotine. Here's another natural product, mescaline. So peyote cactus, those peyote buds that send you on those flying hallucinogenic trips. That's all due to this compound, mescaline. And you can see there's that basic lone pair on there. We already mentioned methamphetamine. That's speed. It's prescribed clinically as Adderall. Maybe there's other brand names for that. You know, a lot of these have recreational, if you'd call it that, use as well. And then caffeine is kind of the outlier. It's not an amine. It's kind of unfortunate that they've ended this with the INE ending, because there are no basic amines on this nitrogen, and it is not an amine. It's a nitrogen heterocycle, just like the purine and pyrimidine bases on DNA. If I look at this, the most basic nitrogen lone pair is the one here, not the one on the top, because by resonance, it's donating to the one down on the bottom, and you don't see donation going the other direction. All the donation goes from this lone pair down to the bottom one. And you can draw a resonance structure if you wanted to. But of course, everybody knows that caffeine is the main active component in coffee. And then we get to some more powerful drugs, like ones that bind the mu-opioid receptor, like heroin. The acetyl groups are added using acetic anhydride on either commercially or by illicit labs. And that allows it to cross through the blood-brain barrier before it gets deacylated and converting to the active form morphine, which binds to mu-opioid receptors and makes you feel probably very good. All right, now let me go ahead and draw. I have to draw triethylamine here because in the lab, this is the most common weak base that we use in the laboratory because it's soluble. This is triethylamine. It's the most common organic base, way more common when you go into an organic laboratory than sodium hydroxide or potassium hydroxide, which are not soluble in THF or dichloromethane or all the organic solvents that we use. So again, what you'll find is the book tends to use sodium hydroxide for everything, but why would I want to put a nucleophile into a reaction where all I wanted was a base? That's why triethylamine is, it's a little bit hindered, so, and it's just a very inexpensive base that's soluble in all organic solvents. Okay, so those are kind of interesting amines. Let's go ahead and start talking about chemistry. And it's what's weird is I'm going to tell you about some chemistry that doesn't work well. The book just, I feel like this is a more complex scenario than it needs to be. But whenever I see an amine, I want to use that as a nucleophile. Amine lone pairs are basic. It means they do proton transfers. They act as bases and pick up protons. And they are nucleophilic, which means they attack carbon. Proton transfers are fast, but attacking carbon and making bonds to carbon, that's slow relative to proton transfers. Let's go and watch what would happen if I took an alkyl amino group and I wanted to do an SN2 reaction. Boy, that sounds pretty easy to do, right? Seems like if you've got an amine and you know it's nucleophilic, it ought to be simple to do SN2 chemistry. It's not that simple. Here's the problem. The problem is you'll have no problem if you mix an amine with an alkyl halide doing an SN2. You'll get some competing E2 elimination. Okay, let's just set that aside for now. I don't want to talk about the weaknesses of SN2, but you'll get a little bit of E2 elimination. But let's just focus on the SN2 reaction here, because the SN2 process generates initially not a new amine. It generates an ammonium compound. See those two H's that are on there? They're still going to be present on this initial product that you get. Let's draw those two amines. And if the nitrogen was neutral before as an amine, when I put that fourth bond on there, it better have a positive charge. So we'll end up generating this alkyl ammonium compound. And as soon as the first molecule of alkylamine attacks the first amine, there's going to be one molecule of this ammonium compound and a bazillion molecules of this amine left over. So I'm just going to draw some of those other molecules of amine that are still floating around. And if you have other molecules of your amine starting material floating around, it's faster for this to do a proton transfer and pick up a proton off of an ammonium compound than it is to attack carbon. Attacking protons is faster than attacking carbons. So even though you would like your next amine molecule to attack an alkyl iodide, unfortunately, as soon as it sees an NH on an ammonium, it's going to pick up a proton. And that's not what you want to happen. You want your amines to attack carbon. You do not want your amines to attack ammonium ions and pick up a proton. That's really inconvenient. So very quickly, you generate an equilibrium. As soon as you start adding an extra alkyl group, you've now generated this equilibrium mixture. It'll be about 1-to-1. The equilibrium concept will be about 1-to-1. Now, right, very early on, as soon as you generate an amino group, it's going to get this ethyl ammonium product is going to end up getting deprotonated. And now you have to worry about that stupid lone pair there that's still there on the product. Oh, this is awful, because now, in addition to your amine floating around, that's what you want to act as your nucleophile. Now you have another nucleophile floating around. It's your product now. It can attack again. You can't stop this. That's supposed to be a lone pair. How do I draw that more like a circle? There we go. That lone pair is now going to come and attack. So now every ethyl iodide molecule has a choice between being attacked by one of the amine starting materials or this ethyl amino group. And it turns out that the more alkyl groups you put on amines, they become slightly more nucleophilic. So even if they were present in equal amounts at some point in the reaction, this would still have a kinetic advantage. And so you end up adding a third alkyl group on that nitrogen. Now initially, as soon as you put that fourth bond on there, that's going to have a positive charge. But remember, if this is floating around in the presence of your amine starting material, then it's going to get deprotonated. Let me go ahead and draw another one of these amine starting materials on there. It's all in equilibrium, all of these amines and all of these ammonium compounds, and you cannot stop this from happening. You can't stop all of these amines from deprotonating ammoniums and back and forth and back and forth. And so this will now generate even more of this mixture. So now your amine starting material is just starting to get protonated, and now you've generated yet another nucleophile that you didn't want in your reaction. So if you thought you were just going to do a simple SN2, now you've got over-alkylated product with not just one ethyl group, with two ethyl groups, and this is still nucleophilic. It is still capable of acting as a nucleophile. And so you'll still see additional SN2 reactions where your tertiary amine attacks and picks up, and that's the end for that, right? You thought you were going to go into the lab and do a simple SN2, but you get this uncontrolled mixture where your products have one ethyl group, two ethyl groups, even three ethyl groups, and there's no way to get rid of this positive charge. This is what you would have at the end of the reaction. You can't neutralize it. You're just going to end up with a salt, and it will stay in the aqueous layer, and you'll never get it out. So if you like generating horrible mixtures, this is a reaction for you to use. I don't think I've ever in my life asked you, how would you generate a horrible mixture? I usually ask, how would you efficiently do something? So my advice to you is avoid. If you want to make carbon-nitrogen bonds, I would say avoid this. Let's go and talk about some of the solutions. So how do you make carbon-nitrogen bonds? How do you synthesize amines? And amines are good nucleophiles. How do you synthesize amines without using this lame SN2 process that generates mixtures, that generates horrific mixtures, disastrous mixtures? I can't emphasize enough that you should avoid that. Don't write that down as a step. If I ask you to suggest plausible reagents for efficiently doing something, don't use SN2 reactions of amines. It's not an efficient way to do that type of chemistry. Sorry, I've got some. Okay, so what are some strategies? If you felt like you wanted to do this, if you wanted to do some sort of an alkylation where you made a primary amino group, right? And I'm telling you what's happened. If you just try throwing in one equivalent of ammonia, you're going to end up with one propyl group, two propyl groups, three propyl groups, just a statistical mixture of all those different types of substituted amine products. So let me show you a strategy that was developed like more than a century ago. It's becoming less and less important, and within the past 5 years, it's not the major way to do this type of chemistry. But the book still presents this as a way to do this one type of transformation where you add an H2N group without using ammonia as your nucleophile. And if you wanted to add this, instead of using ammonia to do an SN2 reaction, there's this reagent that comes from an imide. And in particular, this imide, notice the word, the ending IDE. Let me underline that in red. That's called an imide if you have two carbonyls on an NH. Sorry, that double bond up here doesn't look very good. And these are easy to deprotonate. So easy to deprotonate. Because there's two carbonyls, each lone pair on the night, well, one of the lone pairs is donating into not one carbonyl, but two carbonyls. So it's so easy to deprotonate and make this into an effective nucleophile. So I can come up with my propyl bromide reagent, and this will do an SN2 reaction. Now, normally, if you have a lone pair on a carbonyl like an amide, it's not capable of doing of being nucleophilic, but there's still a second lone pair that's sticking out in space and is not conjugated to the carbonyls. And so you get very clean SN2 reactions using this phthalimide. It's weird. It's called, the spelling is PHTH, phthalimide, but nobody said, just ignore, don't say the PH. Nobody says the sound, they just say phthalimide. You don't pronounce the PH. So this is a phthalimide anion. And there's a two-step process for doing what you can't easily do, or that has additional complexities with if you tried to do this just using ammonia. So you get a clean SN2 alkylation. And I'll just write clean SN2 with no over-alkylation, not even one extra molecule of alkylation, because once this alkylates, clean. No over-alkylation. You get clean alkylation, and that is never going to alkylate again. The lone pair that's left over on here can't alkylate anything. It's donating into the two carbonyls. So this will just sit there at the end of the reaction. But the problem is we've got these extra two carbonyls on here that we don't want. So I'm going to show you some conditions for hydrolyzing they're essentially amide, like amide bonds. The first bond hydrolyzes easily. It's an imide bond. So we can use the same conditions we use for hydrolysis of amides. And the conditions that I gave you for hydrolysis of amides This is not an amide, it's an imide. This functional group where there's nitrogen with 2 carbonyls. We use 4 molar sodium hydroxide. That's not a good A. We use water, and we use heat, 100 degrees. You got to boil it overnight. I'm not going to walk you through the mechanism. It's a 12-step mechanism. It's like that. It's just not worth us walking through. And so the products that you get out of this are your amine. There's the amine we wanted. And it took 2 steps, but it's clean chemistry. And so that's the advantage of this process called the Gabriel. This is called the Gabriel synthesis of amines, of primary amino groups. And we have better ways to do this. The other byproduct you get would be the products of kind of amide hydrolysis. Again, this is not an amide, it's an imide, but they look like the products of it. And when you hydrolyze amides under basic conditions, you get the neutral amine and you get the carboxylate minus salt. You don't get the carboxylic acid because the conditions, whoops, are basic. And so with the sodium hydroxide, you would get the disodium salt of the phthalic acid. Okay, so I've written a note here just to remind you, sometimes when I ask you for reagents, like on the exams, I'll have a box and say, how do you go from here to here? What are the reagents? Don't just write hydroxide minus. That's not a reagent. We have no bottles in the laboratory that say hydroxide minus. Or you can't go to a chemical company and say, I'd like to order some HO minus. They'll say, what? So if I ask you for a reagent, it has to be something that I can buy or something I have as a label on a bottle on my shelf. Reagents would be sodium hydroxide or potassium hydroxide or ammonium hydroxide, not just hydroxide. All right, that's the Gabriel synthesis. I can't resist telling you what is the more common way to do this. The more common way to do this would be to use azide anion. You can buy bottles of sodium azide. They look like this. They've got a weird looking resonance structure that looks like this. And this is what we do nowadays. We do this. We don't generate sodium or potassium phthalimide in the lab. We do SN2 reactions to make alkyl azides, and then we hydrogenate those. Don't worry about the functional group. And then we use hydrogen and palladium on carbon. That's the modern way we do this. And there's no byproduct except nitrogen gas. So it's so clean to do this type of chemistry here. I mean, can't think of anybody who's done a Gabriel synthesis in the past 10 years or even 20 years. People have switched over to sodium azide. All right, and that's all we have time for today. When we come back on Wednesday, we're going to start talking about the chemistry of nitro group reduction, some other ways to make amides and amine functional groups. My team and I were working very hard on getting the practice exam for exam 2 up onto sapling. Our exam 2 on Friday is going to be done using sapling, and hopefully the exam 2 practice exam will look very similar in format to exam 1. And when you take your exam online on Friday, you'll think, wow, the format is exactly the same as, or very almost the same as the format of the exam that I took the first exam in this class. We don't want you being caught off guard about the format of our tests. It's the content that's going to be different. You won't know what the questions will be, but the style of the questions should not be sucking up your time on when you take exams remotely. All right. It's a glorious day here in Southern California. I realize it's raining. Imagine that here in Southern California. That's a good opportunity to stay inside and do some organic chemistry. Start working some problems from the back of chapter 25. All right, I'll see you guys on Wednesday.